beat frequency. This is a nice little way to finish off the interference of waves. Okay, so I want you to imagine two waves. I'm going to draw one in red. Now I'm going to draw it with I'm going to try to draw it with a specific frequency. I'm not going to do that. There we go. Okay, so here's a wave. Let's say this is a sound wave at a particular frequency. Well, if we had another wave that was close to it, but not quite the same frequency, so a little bit longer frequency, something like this. Maybe I'm going to draw these a little bit longer to get the effect, and this is the short one. What I want you to notice is these two waves were sounding together, or if the two waves were in the air at the same time, they would interfere with each other, wouldn't they? And so when they interfere with each other, we would kind of have to put one on top of the other and kind of superimpose one on the other. But if we look at it, what we can see at the beginning is the crests are kind of lined up. And if the crest is lined up with the crest, we would expect that to be pretty constructive interference, and we would expect the result of these two waves to be louder, higher amplitude. But because one wave is a little bit different in frequency than the other, it's not long before we see in this region, right here, that most often it's crest on trough that's overlapping. See that? Crest and trough, which means that in this part of the picture, we would have more destructive interference here, which would result in a sound that is not as loud. So at the start, we had constructive interference because it was crest on crest. But then, after that period of destructive, and in fact, we start to notice it right here, go back to a spot where now it's trough and trough, right here, crest and crest for the most part. We see that we have another constructive area of interference. And if I drew the picture continuously, you'd see that there would be an alternating pattern where the waves would at some points match up constructively. So this word here was constructive, like here. But then shortly after that, they would fall out of phase and be destructive. And then they would be constructive again. And then destructive and constructive and destructive and constructive. The resulting wave that you would hear would be a wave that had a large amplitude at first, but then pretty much went to a small amplitude of interference when it's destructive, and then a large one again, and then small. And you would have areas where you would have loud sound, louder, and areas where you would have quieter sound. And then what would happen is you would be able to specifically hear the sound getting louder and quieter, louder and quieter. So I'm going to try and do that as a demo with the tuning forks. You won't be able to see this, but if you listen, you'll be able to hear exactly what I mean. So I have two tuning forks here, one of which I can tune down so that it's out of phase with the other. Okay? So now when I sound them together, and listen carefully to the sound you get, here's one, and now the other. And if you listen, you can hear that pulsing in the sound. It's actually a louder, quieter, louder, quieter. I'll do it again. First one, now the next one. It's like a throbbing in the sound. It's kind of annoying. Right? Yeah. Well, that's because what your ear is hearing is the loud and soft sections. Now, here's the interesting thing. A wave with loud and soft sections has a sort of a different frequency altogether. There's a frequency of the wave bumps, the regular frequency of the wave, which doesn't change. But there's also a frequency of how often the loud parts come in between the soft parts. That's what we refer to as the beat frequency. And we call this throbbing sound that we heard beats. And the reason it's useful is because if the two waves are very close together, like I have done with beats, the beat frequency is fairly low. 1, 2, 3, 4, 5, 6, maybe 1.5 to 2 hertz at most. But if the waves are not as similar, let's say that one frequency is quite a bit different, and I'll do that by adjusting the tuner on this fork, so that now I've made the two frequencies slightly further apart. Listen to the frequency of the beats. You can hear the pulsing has gotten faster. The further apart the frequencies are, the faster the pulsing will be. Right? That frequency pulsing is probably at least 3 or 4 times a second. Right? Let me do it a little bit more. Still quite annoying though, isn't it? Still quite annoying. Let me adjust this one a little more. Now they are even further apart, the frequencies. And you can hear the beat frequency is quite fast and very annoying. However, there's an interesting thing that happens with beat frequency. At first it's annoying, but if I move these tuners quite a bit, so now the frequencies are very far apart. So far apart that they would be considered vastly different notes on a musical scale. The beat frequency becomes so fast, it's more like almost like a buzz. And in fact, it sounds quite nice to the ear. Listen. The beat frequency has gotten so fast, it sounds like almost a pleasant kind of buzzing sound. And of course, what that effectively results in when we listen is what we call harmony. Two notes that sound nice together because they produce a very pleasing, buzzing beat frequency are, how we say, notes that are in harmony. So here it is even further apart. Most of us would agree that's far less unpleasant. In fact, it's kind of nice, isn't it? So we hear this harmony sound. So beat frequencies that are very close together are annoying. Beats caused by notes that are close together are annoying. But beats caused by more distantly separated frequencies can be quite pleasant and produce harmony. So this is useful to a musician who's trying to tune an instrument. If this is the tone you want, and you're checking this other one to see if it's in tune, when you play them together, you'll get a beat frequency. Now it's very slow. The slower the frequency, the closer they are to being a match. So what you do is you adjust your instrument and you bring it a little bit closer. You can adjust the tuning by changing tension on the string or perhaps changing the length of your resonating air column slightly, whatever, until you get them to sound like this. Almost completely disappeared, and we know that the two notes are the same frequency, or they are in tune with each other. So that's what, when you're tuning an instrument, you're listening for those beats. And the faster the beats get, the more out of tune you actually are. And you can bring the notes into tune by reducing the beat frequency. And so we can easily calculate the beat frequency. It's actually quite simple. Beat frequency is equal to, and we're going to use absolute value signs here, which means that basically what it is it's the difference between the two frequencies involved. And the absolute value signs mathematically mean that it doesn't really matter which way you subtract. all it really means is subtract the smaller from the bigger. Always put the smaller one here and the bigger one here. Now, if you do that in regular math, you'll get a positive number or a negative number, right? But if you always put the smaller here, that's what absolute value allows you to do. It allows you to find just the magnitude of the difference between the numbers. It doesn't matter whether it's positive or negative. So, for instance, if you had a frequency 1 of 620 hertz, and then you played along with it frequency 2 of 627 hertz, right? You would simply do the beat frequency as 627 take away 620, which equals 7 hertz. So you would hear throbbing or beating about 7 times a second, a 7 hertz beat frequency. But if your first frequency happens to be like this, watch. Let's say frequency 1 is 627 hertz, and frequency 2 is 620. Well, then when you do the formula, the beat frequency, in this case it would be 620 minus 627, which actually is negative 7. But these magic absolute value signs take away the negative sign. They say, don't worry about whether it's plus or minus. The answer is still 7 hertz. Right? So you can, if you look at this, I could have written 627 minus 620 and gotten the same answer. So the order of the subtraction should always be bigger minus smaller, and then you don't have to worry about the absolute value whatsoever. But that's how it works. And some of you might have seen that in your math classes. And so that's it. Here's a common question that we ask on tests and things about beat frequency. So here's how you get an example. Two tones are played together. One has a frequency of 510 hertz. A beat frequency is heard. A beat frequency of 12 hertz is heard. So the question is, what is the other frequency? So if the beat frequency is equal to the difference in the two frequencies, it's pretty obvious then that if the beat frequency is 12, you have two possible options. That's what the absolute value is. It's kind of weird. If the beat frequency, did I say was 12? Check my numbers. Yeah, 12. Then we know that one of the frequencies is 510 hertz. So it could be 510 minus the other frequency. Well, let me just change that since I put it first. I wrote that one first, so I'll call that one. It could be this, right? Or it could be the opposite. So the answer in this case, if you just solve this as an equation, F2 minus 510, well, you would add the 510 to the other side and you get 522. And that makes sense because the beat frequency is the difference between them. So the difference between 522 and 510 is 12, right? However, what if it's on the other side of 510? Instead of being 12 higher, it could also be 12 lower and have the same difference. So you have to consider that the 12 could also be the absolute value of this, and it could be the other way around. In which case, what you would get, well, to be honest, what I should do is I should write it like this. I'm kind of cheating on the math because I know many of you haven't done absolute value before. So here's one way to do it. The other way to do it is to realize that this could also have a negative answer. So it could work out to negative 12. So you could write negative 12 equals F2 minus 510. And then when you put it over to the other side, you're actually subtracting. And if you subtract that, you're going to get, what, 498, right? Equals F2. 510. But it's actually easier just to kind of think about it in your head. If the beat frequency is 12, then the other frequency has to be either 12 above or 12 below the frequency you started with. So we started with 510. If there's a beat frequency of 12, then it must be either 12 above, which is 522, or 12 below, which would be 498. So you can do it that way, which is much simpler. And that's really all there is to beat frequency.